So I'm assuming you are having time to read it. So I think we can, looks like the recording has started, so we can proceed. Just confirm again that you can see my, screen.
Yes, we can see.
Okay, so today I think this is why we stopped last time.
Can see it.
So today we shall move to the symmetric group. So we start with the definition. We define a permutation. There should be a space between the A and the word permutation. So this, or rather we can just remove the A and leave permutation. What we are defining here is a permutation. So a permutation on n symbols or on n objects is a function from a set with n elements to itself. So it's basically a one-to-one and onto function from a set to itself. Some people are still joining. So if you consider a set which has exactly n elements, and then we denote this set by Sn, we call it Sn. So this Sn, no. The set is X. X has n elements. And then we create a new set Sn, which consists of all the bijective functions from X to itself. So all these functions from X to itself, we call that set Sn, and we claim that Sn is a group under the composition of functions. So this is a symmetric group, the set of all bijections from X to itself. We shall just do a small sketch of the proof that this is a group. So here we go. So if you pick any two bijections from a set X to itself, then their composition will still be a bijection. So closure is proved here for a group. If you composition of functions is associative, so this one you learned in basic mathematics. You can go and get the details for that. The identity map here will act as the identity element of the group, and that means if you compose any, can you hear me?
Yes.
Yes. So if you compose any function with the identity map, you don't change that function; it remains intact. So the identity map turns out to be the identity of the group, and since all functions that have been picked were bijective functions, their inverses will also be bijective. This should be small n, not capital N, since throughout we are working with small n. So I will correct this before I share the slides. So we look at some examples here, or rather one example. So if you consider the set with exactly 3 elements, we choose to label the 3 elements in the set as 1, 2, 3. Now, this labeling is not mandatory. You can use any labeling, but this is convenient for us because you can keep track of the objects if you label them as 1, 2, and 3. So here the numbers 1, 2, and 3 are not representing numbers. They are just labels for 3 objects. We use them because it's easier to keep track of the numbers, but otherwise here they are not really numbers. They're just labels for 3 objects in a set. And then we list all the bijective maps from X to itself. So we had done this before. We label them differently, but we had done it before, and this is exactly the same as D3. So D3 and S3 are the same, But when n is bigger than 3, that changes. S4 and D4 will be totally different. We shall see why in a short while. But these maps, we had looked at them before, so they're familiar. They're just the same maps in D3. Now we have relabeled them because we want to think of them as elements of S3, the permutation, the symmetric group of degree 3. So the symmetric group S3. I think there's some people trying to join again. There you go. So there's nothing new here. I think you know how these maps work now, right? So you can, yeah, there's a total of 6 bijections from this set X to itself. We learned how to count the number of maps. I think at least the group I taught, I'm sure we did that. We learned how to count the number of injective maps from one set to another. So you should be able to count the number of maps from X to itself, and you'll end up with 3 factorial, which is 6. So if you get all the, if you construct a total of 6 bijections, then you have all of them. Are there any questions on this? So we have relabeled them. They are precisely the same maps we had in D3, but now we have them labeled as E, sigma 1, sigma 2, tau 1, tau 2, and tau 3, using these new Greek letters. So these 6 elements, they form the group S3, the symmetric group S3. Are there any questions? So the same elements in S3, we can write them down as follows. So the identity element is the one that sends every element to itself. So we just write them in this form. We put brackets and 2 rows. Then the first row will contain the 3 elements. Second row gives you the where each of the elements is sent by the map. So the identity map sends 1 to 1, sends 2 to 2, and sends 3 to 3. You can go back to our visual notation. So this becomes your identity map. You simply write this as your first row and that as your second row. You do the same for all the others. So for instance, for tau 3, I will pick this as a first row and this as a second row. Then my new notation will look like this. All the elements will now be written in this notation. This is called the 2-line notation. Some books may call it different things, but we can call it the 2-line notation. So the same maps can be represented in this manner. So it's just another way of writing the same maps. Right? So you can take some time to look at this so that you see what is going on. If we go back again, just to be, let's pick one of them. Let's pick sigma 2. Sigma 2 sends 1. We have 1, 2, 3. And 3, 1, 2. So this 1, 2, 3 will be our first row, and 3, 1, 2 will be our second row. So let's check if we got that right on this end. Yes, 1, 2, 3, and 3, 1, 2. So all the others are done the same way. And then you have a new notation. Sometimes this notation is also convenient. Now, remember we learned how to get the composition of these functions earlier. So in your own time, double check that the composition of sigma 1 and tau 2 should be equal to tau 1. I hope I got this right. So double check. If there are any mistakes, you should be able to figure out, because now you know how to get the composition of functions. We did this earlier. So check that this actually works. You can try out other compositions that are not listed here for your own practice. So we can count the number of elements in Sn. So it turns out that the number of elements in Sn will be n factorial. We also learned how to do this in first year, how to count the number of injective maps from a set to another set, finite set. So we consider this set Sn. The elements of Sn are the bijective functions from set X, which has n elements, to itself. Remember, we said that earlier. So the number of such functions will simply be given by this formula. Now what I suggest is that you go back to your notes on discrete mathematics and see how we compute the number of bijections, or rather injections from one. You just need to focus on injections because this map is from a finite set with it to itself, and any bijection will also be an injection. So you can count the bijections by just counting the injections. Injections means the one-to-one maps. Are we together? You can hear me?
Yes.
Okay. So you will have to find time to read through these things. You really need to internalize them for them to become familiar. So you have to read this over and over again. There is really no shortcut. You have to read them over and over, and don't read them like a bedtime story. Get a pen and a paper and write them down so that they make sense. So here we have established that the number of elements in Sn will be n factorial. We've already seen S3 and listed all the elements in S3. So we'll give you some work. So S4 will have exactly 24 elements. 24 is the same as 6 factorial, right? So your work in your own time, try to write down. Pardon?
24 is 4 factorial.
Yes, correct. So write down all these 24 elements in your own time of S4. You make sure you write them because we shall need them for other purposes. So just look for all the one-to-one maps from a set with 4 elements to itself. So you can label the 4 elements 1, 2, 3, and 4. Then you find all the bijections from. So you will notice that S4 is not the same as D4. D4 had how many elements? The symmetries of a square, how many elements did it have? That's it.
8.
That's exactly 8. So it's just a subset of S4. D8 is a subset, actually a subgroup of S4. So you need to find, already you have 8 of them from the dihedral group. So you need to find how many more? 16 more.
Yes.
So do that as an exercise. So the other question I can ask is, how many elements does S5 have?
$20.
20.
20.
What?
Huh?
120. 120.
120. Okay. Okay, that's correct. So you can see how fast these groups are growing. What about S6?
$720.
Correct. So at S6, you're already dealing with very large groups. These groups really grow very fast. So it's very difficult to study them in a manual way. So that's why it's necessary to develop some theory to play around with them and understand them better. If you try to do this manually, it's not possible. They grow really fast. So it's the groups are also very important in many other studies, the symmetric group. So it helps to understand them. In a symmetric group, you can pull out some subgroups, and in particular, a subgroup of Sn will be called a permutation group. So, for instance, D4 and D3 are D4 is an example of a permutation group because it's a subgroup of S4. So here we define what we call a cycle. So if you pick a bijection in Sn, and we have a list of R integers, let's call them x1, x2 up to xr. These integers are from the set of natural numbers from 1 up to n. So these are these integers, they don't have to be consecutive, but they are picked from that set of integers running from 1 up to n. So if it turns out that this map in Sn sends xi to xi plus 1. So for instance, x1 will be sent to x2, x2 will be sent to x3, and so on. And then the last in the list is sent back to x1. And any element that is not in this list is fixed. So if x is not in this list, it does not move. It remains fixed. Right? Then this map is called a cycle of length r, and we denote it as x1, x2, all the way to xr. So the cycle can be written in several ways. You can start at any point. For instance, I could start at x2, and if I start at x2, that means x1 will have to move to the end. It will still be the same cycle. Right? I can start at any point. If I start at xr, then xr moves to the beginning. So xr goes to x1, x1 goes to x2, and at the end, we'll have xr minus 1 going back to xr. So you can start at any of these r elements, and that means there are ways of writing a cycle of length r, depending on which element of the list you choose to start with. Any of them is correct, but most of the time we prefer to start with the smallest number in the list. Any questions on this? We shall do an example shortly. So let's see what the example says. So let's pick this example from S3. 1, 2, 3 being mapped, 1 mapped to 2, 2 is mapped to 3, and 3 is mapped to 1. So if you take x1 to be 1, x2 to be 2, and x3 to be 3, then we have the following situation. x1 goes to 2. In other words, 1 will go to 2. x2 goes to x3. So in other words, 2 goes to 3. And clearly you can see that 3 will go to 1. So what that means is that in cycle notation, you can write it as 1, 1, 2, 3. So instead of writing this whole thing here, you simply write it as 1, 2, 3. So any element that remains fixed is ignored. Here we have a situation where there's no fixed element, so you can't ignore any of them. So, but if this was longer and we had some other elements which don't move, we simply ignore them. We write the cycle as 1, 2, 3. So if you choose to start from 2, you will still get the same cycle, but now you'll have 2 going to 3, 3 going to 1, and 1 going back to 2. So you have 2, 3, 1. You can also start from 3. 3 will go to 1, 1 will go to 2, and 2 will go to 3. So you have 3 to 1, and then 1 to 2, then you have 3, 1, 2, and 2 will go back to 3. So this last one always is the one that goes back to the first one. So you don't have to write 3 again at the end here, because by definition, this last one should be mapped to the first one. So here is another example which leaves a one fixed. One does not move here. So if that happens, we simply ignore one. So 2 and 3 are the only ones that move. So here we end up with a cycle that moves 2 to 3. You can also write it as 3, 2 if you like. But like I said, we prefer to, in the cycle, we prefer to start with the smallest number. So that's how the convention we shall use. We just start with the smallest number in the cycle. You don't have to, but it's what we shall pick as our convention. So here we have a cycle of length 2 in S3. And here we have a cycle of length 3 in S3. I don't know if I have any bigger example. So here is another cycle of length 3 in S3 again. 1 goes to 3, and 3 goes to 2. So you have 1, 3, 2, and 2 goes back to 1. That makes sense? Any questions?
Yes.
You have questions or it makes sense?
Makes sense.
Good. So you should be able to
Makes sense.
You should learn to flip between these two different notations. So you should be able to convert this one notation to this other notation easily. Anytime you have a cycle, you should get used to that. Eventually, we shall start working with this cycle notation and avoid this two-line notation. So if you have a cycle of length 2, it has a special name. It's called a transposition. So here is a theorem which tells us that any cycle can be written as a product of transposition. So if you pick any cycle, it's a cycle of length r, it's possible to write it as a cycle, as what? As a product of r minus 1 transpositions, right? So we have exactly r minus 1 transpositions for this cycle. And this is how the transpositions are. We shall not prove this, but you can take some examples and check that this is true. So now here, what this means, the operation between these cycles is the composition of functions. So this is a cycle that sends x1 to x2 and x2 back to x1 and leaves everything else fixed. So that's the map, this cycle of length 2. This is a map that sends x2 to x3 and does not move anything else. So we are getting a composition of r minus 1 functions. And these are the cycles of length 2. So we will not prove this, but we shall illustrate it using some examples in a minute. So this second one says a cycle of length r has order r. Remember we talked about the order of an element in the group, and the order of an element is the smallest positive integer, such that if you multiply that element by itself, that number of times, you should get the identity. So if you have a cycle of length r, if you compose that cycle with itself r times, you will get the identity. And r is the smallest number of times you can compose that cycle with itself to get the identity. So the order of a cycle of length r is r. Okay. So now to get the inverse of a cycle is this simple. You simply rewrite the elements in the cycle in reverse order. Then you get the inverse. So if you compose this element x1, this cycle x1 xr with its with this other cycle, which is just a reversal of the elements in the first cycle, you will get the identity. There's this other, if you have any permutation in Sn, so you can get its inverse, F inverse here. So if you get the composition of this permutation, a cycle of length R and the inverse of F, it will turn out to be a cycle of length R, and the entries in the cycle will be the image of X1 under this permutation F, the image of X2 will be the next one under the permutation F, and so on, all the way to the last one, which will be the image of XR under the permutation F. So this is a permutation of three, this is a composition of three functions. So F is any permutation in Sn, we don't care what it is. But this second one is a permutation, which is a cycle of length R from Sn. And on this end, we compose with the inverse of F. When you do this, you also get another cycle of length R, and these are the entries in the cycle. So I think these are the only properties we list in this theorem. You can, there are many others, but I will leave them out for now. I think these four are what we need for our purposes. Again, we shall not prove this, but we can illustrate them using some examples. So here's an example. This cycle of length 3 can be written as a product of transpositions 1, 2, and 2, 3, using the same ideas from this theorem. So applying this idea here, we can write any cycle as a product of transpositions. Remember, transposition is simply a cycle of length 2. So if you compose this, this is a cycle of length R. If you compose it with itself 3 times, so I've used cubed here to mean compose this cycle with itself 3 times, you will get the identity in the group. So this cycle of length 3 also has order 3. So that's the second part of the theorem, which says a cycle of length R should have order R. So you can do that in your own time. Compose this cycle of length 3 with itself 3 times, and you should get the identity in S3. So if you want to get the inverse of 1, 2, 3 in S3, you simply reverse the order of the elements in there. So this cycle 3, 2, 1 is the inverse of 1, 2, 3. Now remember, we prefer to write the cycle starting with the smallest number in the list. So in our case, the smallest number is 1. And if you write the cycle starting from 1, it means 1 will go to 3, and 3 will go to 2. So we'll end up with 1, 3, 2. So it's just the same cycle, but we choose to write it starting from the smallest number in the list. So this illustrates the, was it the third property? Yes, if you want to get the inverse of a cycle of length R, you simply write it out as the same cycle in reverse order, starting from the last one all the way to the first. I don't know if this is one more illustration of finding the inverse. So the inverse of, think of this as a cycle in S8. So its inverse will simply be the same integers in here in reverse order, 8, 7, 3, 2, 1. Now again, we prefer to start with the smallest number, so we can write it as 1, 8, 7, 3, 2. But this is still correct. It's just that for us, we choose to start with the smallest number in the list, in the cycle. Any questions on this?
Hello, sir.
Yes.
for part 2. Can we just do one part so that we can know how to decompose that function?
We already saw how to do compositions of functions. So I suggest that you go back and watch that video. We did many examples where we were getting composition of functions. So this function 1, 2, 3 is this one. We have already seen it here. This one, sigma 1. We also wrote it in a different way. It's this function here. So compose this function sigma 1 with itself 3 times. It's the same thing.
Oh, okay, again.
Okay. We have done this. We did many examples. I think you just go back to the video and watch it. Make yourself a nice cup of coffee or your favorite drink. Is it porridge?
Yes.
Yes. Make some porridge, then you sit down with a pen and a paper and write things down. When you write things down, you understand them better. So where are we? I think this point now. Is there any other question on this? No questions? So if you have 2 cycles in Sn, not necessarily of the same length, so this first cycle is a cycle of length R, and G is a cycle of length S. So we say the cycles are disjoint if they don't have any elements in common. These 2 sets don't have any elements in common. So none of the numbers here will appear here, and vice versa. And none of the numbers here will appear on this end. So if the intersection of these 2 sets is empty, then we claim that these 2 cycles are disjoint. So let's look at an example. Let's consider these 2 cycles. This one that sends 1 to 3, and 3 to 4, and 4 will be back to 1. So this is a cycle. We have a second cycle sending 2 to 5, 5 to 8, 8 to 7, 7 to 9, and 9 back to 2. So we can think of these as cycles in S9, and you can see that this second set is a cycle of length what? Length 5. This first one is a cycle of length 3, and they don't have anything in common. If you take the set consisting of the numbers 1, 3, and 4, and the set consisting of the numbers 2, 5, 8, 7, and 9, those 2 sets have nothing in common. The intersection is empty. So these are an example of disjoint cycles in S9. So we have a theorem here which says that disjoint cycles in Sn will commute. Commute simply means the order in which you compose them does not matter. You will get the same result. So for instance, if you compose this cycle with this cycle, you can do it in any order. Whichever comes first in the composition, you will get the same answer. So we are going to prove this, the fact that 2 disjoint cycles in Sn will commute. So here is a proof. So let's pick 2 cycles that are disjoint in Sn. So here is a first cycle. It's a cycle of length R. Then we have the second cycle, a cycle of length S. So now we need to show that FG, if you compose F and G, it will be exactly the same as G composed with F in that order. So we can check that these 2 actually commute for every element you pick in Sn. So if you pick any element in Sn, it can either be among these ones, the first set, x1 up to xr, or it can be among this y1 up to ys, the set containing y1 up to ys. If it's not in any of those two, it will be outside these two cycles, right? So let's first check for elements that are outside these two cycles. So pick any element, any number m that is outside these two sets, this integer m. So m will be one of the integers running from 1 up to n, because you're working in Sn. So m will be one of those integers. But now we are picking one that is outside these two sets. Now, because any element that is outside these two sets will be fixed by both cycles, we have the following situation. So if you compose f and g, now here we are composing f. Fg means the composition of f and g in that order. So it means g will act first, followed by f. So f composing f and g, the composition of f and g acting on m, where m is not in any of these two sets, will be given by this f of gm. But now, since m is not in this set, it is fixed by g, right? Remember, we say that anything that is outside this set will be fixed by this cycle. So g of m will just be m if m is not in here. So we can replace g of m with m. Again, we have also seen that m is not in this. We have picked m outside this set also. So it means f will also fix m. And that means f of m is equal to m. So using the same arguments, you can show that g f of m will also be equal to m. The same arguments, the fact that m will be fixed by both g and m. So if you pick any element outside these cycles, we see that fg will be the same as gf. The composition commutes. So now let's check what happens if for the other element, if m is in the set x1 up to xr, what happens? M will not be in the set, it will not be in this set from y to y1 up to s, because we have picked these two cycles to be disjoint. Right? We have assumed that the cycles are disjoint. Right? So it means if m is not in this set from y1 up to s, it must be fixed by g, because g fixes anything that is outside that set. So it means gm will always be equal to m. M will always be fixed as long as m is inside this set. So in that case, we can check that f of gm will be equal to f of m. And also g of fm will be equal to fm. The reason now g will fix any f of m will be retained within this set, right? To be one of the elements in this set. Because this is a cycle, anything inside this set doesn't get out. Now, so it means it will also not be in this second set, and therefore will be fixed by g. So f of m will always be fixed by g, because g and f are disjoint cycles. So that g of f of m will always be equal to f of m. What about if you have f of gm? Or rather, we already checked that fgm will just be equal to f of m, right? And g of fm will be equal to f of m. So both fg and gf give you the same result. This is true because f of m will always be in this set and therefore must be fixed by g. So again, if you pick an m that is in the set of the numbers in this cycle, we see that fg gives the same result as gf. they both give you f of m. So you can just mirror the same argument. If you pick an m that is in this set, y1 up to ys, the same argument you have used here will give you fg of m will be equal to gm, and this will be the same as gf of m, using the same argument completely. The reason you can do that is because gm, anything picked by g, will always stay within this cycle. So you'll never find it among these elements. So g of m will never be in this cycle. So it will, g of m is fixed by f, and g of m is also inside this cycle. So it is fixed by, yeah, it's fixed by f. I think I'm repeating myself. But now you should see that we have tested this for all the elements in the list of numbers 1 up to n. So for all bijections, I mean, we have checked this for all possible elements in the domain of these bijections, and we have seen that for all those elements, fg and gf give you the same answer, and therefore we can conclude that for all these two disjoint cycles commute, fg will always be equal to gf. If the cycles are not disjoint, they will not commute. You can test that in your own time. Using an actual example. Let's see. Let's see if we have an example. Here's an example. If you consider S4 and you take F2 to be the cycle of length 2, this cycle 1, 2, and G also to be the cycle of length 2, that is 3, 4, and test this composition. Compose F on G and let it act on every element in this list, 1, 2, 3, 4. So you alternate, check F, if you compose F of G, where will it send 1? And where will GF send 1? Check that and keep doing that until you are done with all these 4 elements. You should see that throughout FG will be equal to GF. FG and GF will send each of these elements to the same image. So this is an illustration of the theorem. This is not a proof. If you asked to prove this, it would just be a net. It would not work. It's an illustration. The proof is what we have just gone through. Please go through this very carefully in your own time so that you can follow it. Are there any questions, please? So, and also be very careful about notation. Here we are picking all the elements in this cycle and writing the set, because we need to refer to the elements in the cycle here. So we write them out as a set. This is not the cycle notation. This is a set of L elements in the cycle of this cycle of length R. Same thing here. This is a set of all the elements in this cycle, all the numbers rather in this cycle. So try this in your own time and confirm that if the compositions send each element here to the same image, regardless of the order. FG and FG send each element here to the same image. They will give you the same permutation. So here is another theorem. It says every permutation you pick in Sn can be expressed uniquely as a product of disjoint cycles up to order. So previously we showed that every cycle can be represented as a product of transpositions. Maybe I can go back short. we made that claim in the theorem before. Let me just go back to the theorem. We have shown that any cycle can be written as a product of transpositions. Now, not all permutations will be cycles, but we can write any permutation as a product of disjoint cycles. What we know about cycles now is that we can write any cycle as a product of transpositions. Here is an example. We're able to write this cycle of length 3 as a product of 2 transpositions, right? So what we are claiming further is that if you have, we have shown that disjoint cycles commute, but then we have also now made another claim here that any permutation can be written uniquely as a product of disjoint cycles up to order. Order means since disjoint cycles commute, it doesn't matter how you order them. You can order them in any fashion you wish. So that's the only difference you can have, but the cycles will be unique. Now this product is called the canonical factorization of F. We shall not prove this, but we shall consider an example. So if you pick this permutation in S8, we can write it as a product of, there are 2 permutations here, F and G. We pick F from S8 and we pick G from S9. So we have written them in the 2-line notation. So we can write them as product of the disjoint cycles as follows. Let's start with F. How do we break it down? So how you do this, you simply start from 1. 1 goes to 3. 2 goes to 1. No, sorry. That's the wrong way. Let's start afresh. We start from 1 goes to 3, right? And 3 goes to 2. And now you take 2 as your next thing to see where it's taken, and 2 goes to 1. So now that cycle is complete. 1 to 3, 3 to 2, 2 to 1. That's the first factor in the canonical factorization. So we stop. Once the cycle is complete, we stop. Then we have to pick something that is outside this cycle. So the next number 4 is outside this cycle. 4 is fixed. No, I've made a mistake here. I should have 5 here. So 4 is supposed to go to 5. So as you write this down, you make that correction. This here should be 5. So 4 goes to 5, and 5 goes to 4. So that's a cycle of length 2, because again, 4 will go back to 5. Remember, this 4 here is a mistake. It's supposed to be 5. So change this to 5 as you write it down. So that gives us a cycle of length 2, and that's the next factor in our canonical factorization. So now we pick any other number that is outside these 2, and the next number we have outside is 6. So 6 goes to 8, 8 goes to 7, 7 goes back to 6. That completes our next cycle factor in the factorization. So the next factor would be 6, 8, 7. So now I'm able to write this as a composition of 3 different permutations. Each of them is a cycle. So this is a cycle in S8 of length 3, 1, 3, 2. So it's a permutation which only moves 1 to 3, 3 to 2, and 2 back to 1, and leaves every other element fixed. Here is a function which sends 4 to 5 and leaves every other element fixed. And this one sends 6 to 8, 8 to 7, 7 back to 6, and leaves all other elements in S8. It will leave all the other elements fixed. So it means I can write this as a composition of these 3 cycles. Each of them is a map in S8. And I can write F as a composition of these 3 disjoint cycles. So we do the same in S9. This G is an element in S9. And we're able to write it as a composition of 2 disjoint cycles. So you can change the order because disjoint cycles commute. So you can actually switch these 2 functions. The order in which you compute them does not matter. So earlier on, I had given you an exercise to write out all the elements of S4. Now you can try, once you write them down, you can now try to write all the elements of S4 as products of disjoint cycles. So that again is an exercise for you. You can do. Any questions on this? Any questions on this? Hakuna maswali?
Can you please present the previous slide?
Pardon? I move back to the previous slide.
Yeah.
Is that the one you want to see?
Yeah, I'm okay. Thank you.
Okay. So, as a consequence of this, it's also possible to express every permutation as a product of transpositions. Now, this product of transpositions is not unique. You can represent it in many different ways as a product of transpositions. But as a product of disjoint cycles, it is unique. So how does this work? Remember, we earlier on said that if you have any cycle, you can write it as a product of transpositions. So we have further said that if you have any permutation, you can write it as a product of disjoint cycles. Now, each of these disjoint cycles can be split further into transpositions. And therefore, any permutation you have can always be written as a product of transpositions. We shall see this in an example shortly. Are we together? So the next claim we have made here is that every permutation can be expressed as a product of transpositions. We have seen how that works. Earlier on, we said any cycle can be written as a product of transpositions. Remember, transpositions are just cycles of length 2. And also, we have made a claim that any permutation you pick can be expressed, any permutation in Sn can be expressed as a product of disjoint cycles. So each of those disjoint cycles can be further split into transpositions, and you end up writing the permutation as a product of transpositions. Now, the writing it as a product of transpositions is not unique. So there's more than one way of writing a cycle as a product of transposition. So that this factorization is just one of the ways, and it's not unique. So what I will challenge you to do is to find another way. Do some research and see how you can write this same permutation as a product of transpositions, but in a different way. And then the number of, you can also have more cycles. So for instance, I can add, I can write, if I add the inverse, I can write the inverse element, which can be written as 1, 2, 1, 2 composed with itself. 1, 2 is its own inverse. So if I add 1, 2 composed with itself on this side, then that still works. I can also fix it anywhere in between, and it will still work. The composition of 1, 2 with itself, because 1, 2 is its own inverse. If you compose it with itself, you get the identity. So if you fix the identity anywhere in between, you get a new representation of this permutation as a product of transpositions, which is not So it's not unique. There's more than one way of doing this. So how do we write this? Initially, we had seen this permutation earlier, written as a product of disjoint cycles. So we can split this cycle into a product of 3 transpositions, that is 1, 4, 4, 2, and 2, 3. And we can split this cycle again further as a product of transpositions. So you end up with this permutation written completely as a product of cycles of length 2. So this decomposition into a product of disjoint cycles is unique, but the uniqueness is up to order because disjoint cycles commute, and therefore I can choose to start with this cycle followed by this cycle. It will still work. But
Excuse,
this,
the theorem is...
Pardon? Which theorem?
The theorem you a while ago, you said you should start with the first element, like in G it's 1 and then 3, but then you've written 1, 4, 1, 2, 4, 2, and 2, 3.
We are writing this. You're mixing up issues. Let's go back here. There's this theorem which says this first part here. If you have a cycle, you can write it as a product of transpositions, right? So if I just have a cycle on its own, this is how I split it into a product of transpositions. So I just consider each cycle separately and write it out as a product of transpositions.
Oh, I've understood.
So for instance, this cycle 1, 2, 3, you can write it as a product of cycles of length 2, right? So that is about cycles. But then we have said further that if you pick any permutation, then you can write it as a product of disjoint cycles. So now each of those cycles, you can split it further into transpositions, and that's what we have done. Yeah. So we have this, we split this G. G was here. G was this permutation in S9. We have split it into a product of disjoint cycles, and now here we are splitting it further into a product of transpositions, cycles of length 2. So this is always possible, right? Any permutation you have, you can first split it into a product of disjoint cycles, then split each of those cycles into a product of transpositions. And that means you'll have split the permutation into a product of transpositions. So the claim, there are two things to note here. This split into product of disjoint cycles is unique. The only thing that can change is the order of the cycles that appear in the factorization. And then, but this one is not unique. There are other ways to rewrite G as a product of transpositions. It's not only one way to do this. The transpositions you can have a different set of transpositions here which will still work. So the challenge is for you to find another set of transpositions which work also. So now another thing we will not theorem, if you have a permutation sigma and you are able to write it in two different ways as a product of R transpositions and also as a product of S transpositions, then R and S are either both even or both odd. So there's more than one way of writing permutation as a product of transpositions, but the one thing that will not change is the number of transpositions in that representation. If you find a representation that has an odd number, any other representation of G as a product of transpositions will have an odd number of transpositions. So the only thing that does not change is that the number of transpositions will be either odd or even. So you can't have a permutation which can be expressed as a product of an odd number of transpositions, and also as a product of an even number of transpositions. They must always either be odd or even. For that reason, we can classify transpositions, I mean permutations, in a short while as either odd or even. So I forgot to write the classifications. So there's a definition which I left out. Maybe it appears later, but I can state it now. So if a permutation can be written as an odd number of transpositions, it's called an odd permutation, right? And also, if it can be written as an even number of permutation, as a product of an even number of transpositions, we call it an even permutation. So a permutation cannot fall in both. It falls in either one or the other. It can only be odd or even. It can't be both. So for that reason, we can look at some examples. Any transposition will be odd. A transposition consists of exactly one transposition, so that makes it odd. Any 3 cycle will be even, since any 3 cycle, say I, J, K, can be written as IJ and JK. So if you have, say, 1, 2, 3, this can be written as 1, 2, as a product of 1, 2, and 2, 3. That gives you 2 transpositions, and that means any cycle of length 3 will be even. So we did this example earlier. We split it into a product of transpositions. Let's see how many there were. You can count. You have 1, 2, 3, 4, 5, 6, 7. So we have written G as a product of 7 transpositions, and that means G is an odd permutation. If this number of transpositions was even, we would say G is an even permutation. But now they are odd, so we'll say G is an odd permutation. You can check, we also have F. You can check if F is even or odd. So the definition came later after I'd already used the term. So this is a definition I was supposed to have put earlier before this example. So a permutation will be even if it is a product of an even number of transpositions, and it will also be called odd if it's a product of an odd number of transpositions. Any questions on this? Yes, Wilbur, you are very quiet today. Hauna swali. Wanashitukan. Why has he left? Anyway,
today I'm taking notes. I'm taking notes today.
You are taking notes seriously.
Yes.
Good. So anybody with a question on this part?
Can you please explain part 1? All transpositions are odd.
A transposition is a cycle of length 2, right? So if it's a cycle of length 2, it's made up of just one cycle of length 2. 1 is an odd number.
Okay.
So as a transposition is just a cycle of length 2. So that's the only transposition in it. So it's made up of one transposition, and 1 is an odd number. So that makes them odd. But here you can see an example, 3 cycles. We have shown that a 3 cycle can be written as a product of 2 transpositions. 2 is an even number. So we say 3 cycles are even.
Excuse sir.
Yes.
Yes. In writing those orders of transposition, like for number 2, all 3 cycles are even. Now, in case you write, because
What
I've
do you
said you
mean
can
by
write,
order?
Yeah, IJ and JK. Is
Mm.
there a difference when you write KJ and JI, or they're supposed to be in that order?
You will get a different transposition. Remember, we have only said the ones that commute. The ones that commute are disjoint cycles. These cycles are not disjoint. You see, they have two elements in common. J is here and J is also here. These ones are not disjoint, so they will not commute. So changing the order will give you a different product. Now, the best thing for you is to compute this yourself in your own time. The experience is the best teacher. So do an example. Pick a concrete example and try it in your own time, and you will see that it doesn't. If you switch them, you will get a different permutation. So the best way is for you to try these things out, not just to imagine them. Pick a pen and a paper and your favorite drink, if it's porridge or tea or coffee, and work this out. And switch off the TV. Is your question answered?
Yeah, I'm okay.
So the important thing, one way to learn these things is do it yourself. If you have such a question, you don't even need to ask me. You try it out yourself. You will see the answer immediately. So we can move on to the next example. So consider this map, which picks, we call the map sigma. So it picks a permutation in Sn and sends it to this multiplicative group. So this is the group consisting of 1 and -1. Under multiplication, just the usual multiplication of integers, this will form a group. Remember, this is a group Z star. I think we saw this earlier in the beginning. If you are considering the integers under multiplication, they will not form a group. But if you isolate the invertible elements, you will only find 1 and -1 as the invertible elements, and those form a group, which we call the Z star. So this is a group under multiplication. And this is also a group, and this is a map from Sn. So we define this map as follows. A permutation will be sent to 1 if f is even, and a permutation will be sent to -1 if f is odd. So the claim is that this map is a homomorphism. I think you can prove that in your own time. Prove that this map is actually a homomorphism. So our interest here is the kernel of this map. So in your own time, please prove that this map is a homomorphism. So one thing you will need, maybe some ideas you can use is because you have to, when you have to prove this, you have to use a product of two permutations in here. So what you need to check is that the product of, if you have two odd permutations, their product will give you an even permutation, right? If you have an odd and an even permutation, what do you get? The product will give you an odd permutation, right? Remember, you're just counting the transpositions. So if you multiply them, you count the number of transpositions. Then what is left? Even and even will give you?
Even.
Even, that's correct. So you can use that to prove that this is a homomorphism. So you'll have to consider them case by case. But the proof of this is also easily available. You can do some research and you will find the proof. So this map is a homomorphism. I can't. Someone is speaking. Would you please put off your microphone so that we can? Huh?
Yeah, the question is, do you pick on any odd numbers or
I can't hear you.
even numbers? Can you pick on any odd number?
You pick on any odd number for what?
To use to prove this homomorphism.
So which odd number do you want to pick?
For example, 3.
So 3, what I want is a group here. So how will 3 form a group? I've told you that I picked 1 and -1 very carefully because I picked this as a group. It is a group under multiplication. So if you want a group here under multiplication and you pick numbers randomly, what will be the purpose of that? You have disappeared again.
No.
So this is a group. I've picked a group here. It's very deliberate, this group I have picked. It is not a random list of odd numbers. It's the group Z star. Okay. So
yes.
We have said this map is a homomorphism, and we have left you that task to prove that it is a homomorphism. So let's now work with the assumption that it is a homomorphism. So if you take the kernel will be the set of all permutations that are sent to the identity element, right? The identity element in this group is 1. So the kernel is all the permutations that will be sent by this map to the identity. And that will be the even, all the even permutations will be the ones that are sent to 1. So the kernel of this homomorphism is the set of all even permutations in Sn, right? So remember, the kernel is a subgroup of Sn. We learned this. The kernel of a homomorphism is always a subgroup of a domain. So that means we have found a subgroup of Sn, which consists of all the even permutations. So one more thing about the kernel, it's also a normal subgroup. So we have found a normal subgroup of Sn. Right? The set of all even permutations forms a normal subgroup. Now it has a special name, and it's usually referred to as the alternating group, and it's denoted by An. So the set of all even permutations of Sn will be denoted by An. Any questions on this? There are no questions. So the important thing here is one, figure out how to prove that this map is a homomorphism. But if you work with that assumption, it's easy to figure out what the kernel is. And then we use the fact that the kernel will always be a subgroup of the domain. So the kernel of this map will be a subgroup of Sn. But we found the kernel to be the set of all even permutations. And therefore, the set of all even permutations of Sn will be a subgroup. In particular, it will be a normal subgroup. And we denote it by An. And it's called the alternating group. So we can apply the isomorphism theorem as follows. Since we have, under the circumstances, this map is surjective. So the image of this map is the whole of this Z star, right? So the image is the whole of this, and therefore, if you apply the isomorphism theorem, the factor group determined by the kernel will be isomorphic to the image, right? It means the number of elements in this factor group, or the number of distinct left cosets of AN, will be the same as the number of elements in this image, right? And that is 2. And that means we have exactly the index of AN in SN is 2. So if you apply Lagrange's theorem, the number of elements in the subgroup will be equal to the number of elements in the group divided. This should be small n, not capital N. I made a mistake there. So don't use capital N. We are using small n throughout for Sn. So the number of elements in the subgroup will be equal to the number of elements in the group divided by the index of the subgroup, which is n factorial over 2. So it means half of the permutations in Sn will be even. That will be n factorial over 2. That's the number of even permutations. So if you're looking for the even permutations, it will just be half of the total number of permutations in Sn. So here is an example for A3. So if you consider S3, the even permutations will just be 1, 2, 3, and 1, 3, 2. All the remaining permutations in S3 are transpositions, so they will be odd. And the identity is also an even permutation. You can write it as a product of 2 transpositions. So the identity is an even transposition, is an even permutation, rather. And this gives you the alternating group A3. So you can find all the 12 elements of A4. I'd listed many of them here, but I think they were cut out. I should, I'll repair this so that we can, when you get this, I share the slides, you will see the missing elements. So we have 1, 2, 3, these 3 cycles. We have put all the 3 cycles. I think these are all of them. You can check just to confirm. All the 3 cycles in S4. Then we have these permutations that are product of disjoint transpositions and so on. So there are more on this side. I need to fix this on the slide so that you can see the remaining ones. But there's an exercise earlier on which asks you to write all the elements of S4 as products of disjoint cycles. And then you'll be able to pick out the even ones, and you can set up A4, all the elements of A4. There should be 12 in total because S4 has 24 elements. Half of that is 12. So you need to find 12 elements, the even permutations. In S4. So that one you'll do in your own time. So you can follow up with some remarks. Now you will note the following. The group A4 has exactly 12 elements. Now 6 is a factor of 12, but A4 does not have a subgroup with 6 elements. You can look up the proof for this. There are plenty of places you can find the proof. Just look online, you will find them. So this is an example to show that the converse of Lagrange's theorem will not work for, or rather may not work for groups that are not cyclic. This A4 is not a cyclic group. Earlier on, we had already proved that the converse of Lagrange's theorem always works for cyclic groups. But if the group is not cyclic, it's possible that Lagrange's theorem may fail. That the converse may fail, rather. That you can have it may fail to have a subgroup whose cardinality is a factor of the order of the group. So it's a group with 12 elements, but cannot have a subgroup of 6 elements. But for cyclic groups, the converse always works. We saw that earlier. So as much as you'd like us to continue, we